Okay, let's see if this works out. I'm just gonna turn off the music and listen to myself and see if this works. Oh, come on. Oh, come on. Yeah, seems to be working fine, just fine. Yeah, seems to be working fine, just fine. Nice, okay. That's great. Okay, so today we're gonna carry on with our Pytorch tutorial, I guess. So I'm just gonna seed into it and see where we are. Let's do this instead. Should be around here. Let's go with this. And I was obviously turned off the whole thing. What is happening? Come to the right. Interesting. Nice. Ah, okay. Open this in code, or Visual Studio Code. Okay, so let's see where we are. We have our PDF here, and we want to... By the way, I added some extra content to the PDF, and you guys can go to the GitHub repository and check that out for yourself. I'm also gonna edit the stream description. Ah, never mind. The description is here. Okay, never mind. That's fine. All right. So this is an example which describes the different Pytorch implementations and also how to create your own data set and so on. So it's a really cool and interesting and easy tutorial on my GitHub. Nevertheless, let's carry on with the explanation. So I think I was at, let's see, we were done with the we were done with transformers, basically. I think. Yeah, so let's go to the tutorials here, and we're gonna build the neural network now. So the neural network comprises of layers / modules that perform operations on data. The Torch.neural network namespace provides all the building blocks you need to build your own neural network. Every module in Pytorch subclass the NNN.module. A neural network is a module itself, and that consists of other module layers. By the way, layers. This nested structure allows for building and managing complex architectures easily. Okay. In the following section, we will build a neural network to classify images in the fashion minist dataset. So this is essentially how we build a network, and I don't think I will... I think I already have this as a example. You know what? Let's build it either way. Yeah. Let's do that. Let's build this network. So we're gonna add a subsection here. Subsection, and it's gonna build the neural network. This is actually gonna have a section. Yeah, and then we're gonna add lsttT, yeah, this kind of tag. I'm gonna end this as well and add this code here. Then I'm basically just gonna explain what it does. Oh, one of my screens just turned black. Never mind. I'm gonna move this back a bit. Just like that, and I'm also gonna close this. So this will essentially import the... Where do I have tabs? Import the OS library, which is the library for the operating systems, and I will probably move this up here. Okay, that didn't really work out either way. Okay, then we will want to import the Torch library. So we import the Torch library, and then we're gonna import the NNN library from Torch. And then we're basically importing the data class, data loader class from torch.utils.data. I'm actually not gonna have that there. And then we also import the transforms library. Okay, then now we should actually get the device, and the device is essentially the per definition what type of unit you want to use to train the AI or the neural network, which is gonna be either your CPU or your GPU. And I will use my CPU here, but you guys can, if you have NVIDIA toolkit installed and you have a NVIDIA GPU or you use AMD, you can essentially use your GPU to use that device or that unit or graphics card or whatever you want to call it. So gonna get this code in here and explain what this actually does. I'm gonna explain for you guys what this actually does as well. So we're gonna simplify it a bit. Okay, that's actually fine. No, okay, alright. Let's do that. So this will check if your GPU if GPU is available, and this will essentially otherwise use the CPU in case GPU is not available. And here if check if multi-process service is available, else use the CPU in case multi-process service is not available. So that's basically what these means. And then if we run this, we will see that CUDA is available if you are using a NVIDIA toolkit. We can actually try this code here. So let's do that and see if this works. Yeah. Let's create a new file here. Not in there. We want to do it in project files. Create a new file here. Let's call this NN creation or something. And then we can type. We also want to. I can actually just check up here, maybe. Yeah. So what we want to do is import the OS library, and we also want to import the Torch library, and eventually also from Torch install or import the neural network library. And here, from here on now, we also want to import, or from Torch utilities, import data loader. And then from there, we want to import also the transforms from Torch Vision. Now, this will only be necessary if you want to use their custom datasets. Otherwise, you probably don't need this. Either way. So let's check the device. So we're essentially just, this is not what I want to do. So we're just gonna check here if we, so if we have, we're gonna say CUDA if CUDA is available. Otherwise we will use the CPU or MPS, I guess. And then we want to essentially also check if torch dot backends.mps is available. Backends.mps. Did they even actually import that in the description? They didn't. Interesting. Either way, we can probably just copy this as well, but I don't think this. And what if I remove these? Okay, let's have these here. They didn't import that. Import this, and this will actually check as well. And yeah, why is there two L's? It shouldn't be any two L's there. That's weird. Let's remove this as well. And then we just want to print the device. So we can just print, and I think we want to using the device, and then that. We also might want to have an F tag here to convert it to a floating string, I guess. Let's do that. And then let's do this instead. One button. I think it is. Nope. It's this button here. Nice. Gonna add these here, and then just add brackets here, just like that, to essentially print the variable. And then I can probably do this also. Nice. Let's see if this runs. Yeah, it kind of did, and we have using the device CPU. It's very nice. I think I also don't need these, actually. Yeah, nice. Okay, so we are using the CPU basically, and it's probably not what you want to do, but in my case I will actually do that. So now we're gonna define a class in the with the Torch library. So we're going to define the class, and we also want to copy this and go here, and we can remove this here. So now we're gonna create another subsection and find the class, and instead of here we want essentially just to have these this code right there. And what this actually does is, wait, I have to do something like that. Nice. So this will obviously create the class itself, and we also have to have an initializing function, because otherwise it wouldn't be a class and the Pytorch library would probably scream at you. And then you have to have a forward. We can actually check what these does. So we create an instance of a neural network and move it to the device and print the structure. So you can see you can also print the structure by moving it to the device like this. But we also define our neural network by subclassing from the nnn.module. And so we create a subclass of that module, which we can change parameters by ourselves. And we also initialize the neural network layers in the init section, or the initialize state section. Every NNN.module subclass implements the operations on input data in the forward method. Interesting, okay. So, every NNN.module subclass implements the operations on input data in the forward method. So let's just copy this text here and use that as an explanation. What this essentially means is that the forward function is essentially an initializing state for the, or it's the, how to speak, it's the initializing state for the operations on the input data that it receives. Which means that based on this code here, this is what type of operations it will do with the input data. This definition or function initializes the different layers in the neural network. So we have, if we go back to the documents here, we actually can see that we have a linear neural network with different dimensions here, and then we have a ReLU, which is a linear function, I guess, and this is also just a linear function. This is a sublinear function, and this is a linear function. And if you want to know what these actually are, I can actually show you images of these, I guess. So a linear function is essentially just we can go to GeoGebra. A linear function is essentially just a straight line. Let me see if I can. So we have a line here. It's basically just a function like this that estimates an estimation based on the slope here, depending on what type of batch sizes you have with all the different points. So this is what a linear. So say you have a lot of points here or data, then this is essentially my friend, you have to understand the logic behind it to actually do the project. I'm sorry, but if you don't want to understand the logic, then how are you possibly gonna do the project itself? Either way, so this linear function here is essentially adjusting the slope here depending on what type of data you have. So that's a linear function. Then, if you want to know what a ReLU is, and this is actually really important because you're gonna use the ReLU a lot, then a ReLU is essentially a linear function like this, but there's a bit, it's a difference between the linear and the ReLU. So I'm just gonna leave this page and go into the next one. So a ReLU is essentially a semi-linear second grade function, I guess. So, and this is basically how it looks like. So, whoops, that's not my intention. So a ReLU, we can actually create a linear function like this, and this will go where the 0 is with the x-axis, just like this. It doesn't really matter, it's something like this. And then you have some input data or batches that looks like this probably, and this is where this is the input data you have, and then you train your neural network so you get something like this. So you have something to this point, and then you have something to this point, and to this point, and then you have something to maybe this point here, and then you have something to this point, and then maybe something to this point, and then you have something to this point, and just carry on like this. And essentially you have a how do you say it? A non-linear function here that adjusts it to the data itself. So this is basically how our ReLU function works. And it's really cool because it can essentially just adjust itself to the different data sets that you input to the neural network. So that's basically how it works. So let's go back to the documentation. So that's why we have both linear and ReLU layers in the neural network. And if we can also create an instance. I'm not going to do that, but we can create an instance and essentially just move it to the device and see how the structure is being used in the neural network, like this. So to use the module, we pass the input data. This executes the module's forward function, which is this function here, along with some background operations. Do not call module.forward directly, which is not the best thing to do, because this is an inserted or already used function, I guess. So we don't want to use this, because then you're gonna break the whole code, I guess. So calling the module on the input returns a two-dimensional tensor with dimension 0, which is essentially so we get a two-dimensional matrix where the dimension is 0, which means that we access the column corresponding to each of the output of 10 raw predicted values for each class, and the dimension 1 corresponding to the individual values of each input. So dimension 0 correlates to the columns, and if we put a 1, it correlates essentially to the direct value in that position in the two-dimensional tensor. We get the prediction probabilities by passing it through an instance of NNN softmax module. Now, softmax is essentially, I can show you guys what the softmax function is, so you guys know. So what it is actually is a mathematical formula like this, but we don't need to know that. You don't need to know the math because we use Pytorch. But we essentially use, where is it? Where is the image I want to show you? If I can just go this, do this. Yeah, okay. So this was essentially what I actually talked about before a bit. Now this, as I told you before, the ReLU will adapt to the different batch sizes or the different data that you have. And that uses also the softmax function, like this, which essentially is changing its slopes depending on the batch sizes that you have. So I might see let's see if we can find a visualization of this. Yeah, okay. This is not what I want. Either way, I will probably show you a visualization of that later. Either way, so let's do this and see. Oh, okay. So it just prints. I will actually just do this to show you guys, but I won't be coding the whole thing by hand. So let's go back to our testing sheet and use this neural network module that we created before. And then we want also to print this module. I'm just gonna show you guys that it works. And essentially, okay, so we are creating our own sub module to this library, and this creates an initial state which modules the neural network by code. So we create a linear layer, a ReLU layer, a linear layer, and ReLU layer, and as you guys can see, it's a, yeah, you guys get it. And then we create a forward definition or function, which is essentially defining the logic to the input data. So this is what the neural network is going to do to the input data. And then we just print the module to see to the device, and then just print it to see how the structure is. So if we run this code, essentially, we will see that it prints the whole structure of this neural network. And as you guys can see, we see that we have a neural network which is using the function flatten that gives us with the start input data with a dimension of 1 and also with a 1 or minus 1. And this is also our linear ReLU stack, which is a sequential operation essentially, which means that this neural network will use different types of functions or layers. What's up, dude? Rodney18, what's up, dude? So this neural network will use different type of layers to calculate or do operations based on the input data that we have. So that's really cool. So we can basically do a lot of different operations with this neural network. But that's about it, basically. So let's see if we can actually do something with this. So to use this module, we pass the input data. This executes the module's forward function, which is the initializing state of the input data, along with some background operations. We can actually check these if we want to. So we get to this GitHub page and see the different operations. So we have set state, get attribute, we have call implementation, slow forward. This is not something you have to know. So this is just the background operations that they use. We don't have to know this, so let's don't bother. And then we can just call the module and returns a 2-dimensional tensor, whatever. We don't really need to know this, actually. We can try it either way. I can explain it to you guys. So let's remove this print here. Yeah, I think that's fine. So we create a variable called x, which is gonna be the training data, I guess, where we randomize. We create a random tensor which has the, I guess if we check here, so the size is 1. The output tensor is going to be 24 or 28. And then we also have the D type, which is going to be 28, and no, it's the layout. And then we also have the, let's see, the device is going to be our current device, which is going to be, for me, our CPU. And yeah, that's about it, actually. So we create this, and then we pass this data to the module. Why is it lagging? To the module, and store it in logits, I guess. And then we have our predicted values, which is where we're gonna use the softmax function to adjust that graph to the current batch sizes. And we're also gonna use the dim dimension layer, which is going to be equal to 1, so we get the specific data. And then we use the argmax to essentially just create the y prediction values, and then we just, or the function result values, I guess. So we get the result values with this function here. So argmax will essentially get the result values, and then we can just print the whole result like this. So let's see if that works. Yeah, so predicted class, we get a tensor of a dimension of 2, which is exactly what they described to us. And yeah, it returns a 2-dimensional tensor with dimension equal to 0, corresponding to each output of 10 raw predicted values for each class. So we get basically a 2-dimensional tensor or two-dimensional matrix from the corresponding. So that's corresponding to each output of 10 raw predicted values. Very easy, very simple. It's not this is not a working neural network at the moment, but we will fix that. So now we're gonna model the layers. So we're gonna break down the layers and essentially tell you guys what the layers is, and I hope you guys understand that. I'm also gonna remove these, remove this. We're gonna remove this as well. Okay, so let's break down the layers and essentially tell you guys what the layers actually do. So we're gonna break down the layers in the fashion minist model that we just created. To essentially illustrate it, we will also take a sample mini batch of 3 images, which is a size of 28 by 28, and see what happens to it as we pass it through the network. So we're gonna test the network and see what happens. So we're gonna create an input image, which is gonna be a random torch tensor, a random tensor with these values, essentially. So let's do that. I'm gonna go to the Python here. Nice. So let's do that. Let's remove this and run the code, and we will probably see that we get a torch size of 3, 28, and 28. Now, what does 3 and 28 means even? Okay, so rand is essentially a function that takes in a series of parameters, but the size is obviously the first parameter, which is 3. So we're gonna have a size of 3 in this tensor. The tensor is gonna be, I think it's gonna be a 3 by 3. Then we have our out, which is gonna be the tensor, and I don't think that really matters. No, the size is actually this whole thing. So that's really interesting. Let's see if we explain this. Let's do this instead. Let's ask Copilot for this. Okay, so this line of Python code creates a tensor named input image using Pytorch, a popular machine learning library. The tensor is initialized with random values. The dimensions of the tensors are 3 and 28 and 28, which I said, which can represent an image with 3 colors, three color channels, which is going to be an RGB color theme, and a spatial dimension of 28 by 28 pixels. The torch.rand function generates values uniformly distributed between 0 and 1. So we create a random image with the RGB color code, essentially. And this can be this can be any type of random images with noise or whatever. So we just create an image basically, and I'm just gonna add this to the latex documentation that I'm creating, and I will essentially explain this code later, or in the explanation later. I don't want to type anything too much. So then we also we initialize the NNN.flatten layer to convert each 2D 28 by 28 image into a contiguous array of 784 pixel values, which is going to be the mini batch dimension at dimension equals 0 is maintained. So we essentially just convert the 2D image to an array of data or values. So let's do that. So we convert the image to an array, which is going to be, I guess, the data for the neural network. So let's do that, and here we can also remove this print here. So this will essentially, this will create an image. So we can create an image with size 3 and also 28 by 28 pixels, and this is also can also be a color code of RGB. Then we also use the flatten, so this will essentially be the flatten tool. This layer will flatten the image, and this will also flatten the image, and also we can print the image size of the flattened image. I just want to mention this, that this layer will flatten the image to an array. So we will flatten the image to the array, to an array, which have 784 values. So let's print this and see what happens. We will probably get the size of the array, and if we want to, why does it? That's weird. And if we, just because it's fun, you know, we can also, I think, if we just print the whole thing, I think we can print the whole thing. Let's see what happens if we print the whole thing. So let's do that, and yeah. So here you have essentially the whole matrix that we got from the image that we created. So what we essentially did was creating a 2D image with different RGB colors by using this. And the reason why I call this a 2D image is because the specific indexes or the specific values has different values that correlates to RGB color values. And then we flatten the whole image, the 2D image, to an array that we can read with the nnn.flatten package. So we get a 2-dimensional matrix or 2-dimensional tensor, which we can use to train our neural network, essentially. So we essentially just converted an image to a tensor, and it's not it's 2-dimensional. Or it's actually more than 2 dimensions now if I think about it. Let's print the size and see what the dimension was again. I think that's how you print the size. Yeah, so we have a 3 by 784 dimensions, essentially. So that's really cool. We have converted the image to an array or a matrix. So that's what we did, and then we used the linear layer that applies a linear transformation on the input using its stored weights and bases. So so we're gonna essentially use this layer here, this linear layer, to do some operations on that matrix that we just created. So I'm just gonna copy in this here, just like that. And we also want to copy it in here. We can also remove this print because we don't need it. So let's remove this. So we create our new linear layer, and I highly recommend that you use the same dimensions as the image, because otherwise it probably won't work. And then we have our out features, which is going to be 20. I actually want to ask Copilot about this line just so I can explain this correctly. Okay, so this line of Python code defines a linear layer for neural network using Pytorch and an end.linear class. The layer is being assigned to the variable layer.1, and here's the breakdown of this component. So this is a class from Pytorch neural network module, torch.nnn. It creates the linear transformation layer with a specific number of input and output features. This layer applies a linear transformation to the incoming data, which is a function that looks like this, and this is essentially the k value and also the m value, so you can define it however you want. But that is essentially what I showed you guys before. And then we also have this parameter, which is going to be the features of 24 by 24, and here you have the whole code actually in the library. Whoops, I just didn't mean to open this whole thing. But here you have all the code. I won't show that. So this parameter specifies the number of inputs features to the layer. In case 24 by 24 or 28 by 28 indicates that the input will be a flattened vector of size of 784, which could represent a 28 by 28 pixel image that has been reshaped into a single vector, which means that we essentially created a layer or module or linear layer that is adjusted to this specific input. Now, if you have other data that you use, then this will probably not work, because this layer is specified to this kind of input. So you have to see where your dimensions are in the different matrices, and also to essentially just adjust the layers depending on what type of data you get into. And here's why data analysis is super important in this topic. Now, this output features, which I don't know what it does, will essentially be explained by this copilot. So this parameter sets the number of output features for the layer. The linear layer will transform the input vector of size 784 into an output vector of size 20. Okay, so it basically just transforms the whole array to an output vector of 20. Okay, that's very interesting. This transformation is achieved through a matrix multiplication with a weighted matrix of size 20 by 784 and adding a bias vector of size 20. So we are essentially just converting a vector by 784, or an array, into a 20 of a size 20 vector, which is really interesting. So we do this by just one layer, by the way. So that's one layer, and usually in a neural network you have multiple layers. So this is very simple stuff, actually. Now we can also, we also I think we tried that. Yeah, we did. Let's just print this again. So as you guys can see, we input this image here. We convert this image by using the flatten package, which essentially will create a 784 size array that we then convert into a 3 by 20 size tensor. So we convert the array to a tensor, essentially. That's what we do. And then, as you guys can see, we can print the size here, and I can also print the whole tensor for you if you want to, which is fine. So this is the whole tensor we get. And as you also can see, the values is between -1 and 1, which means that we also use the flatten and normalized the whole thing. And this is what softmax and flatten does. They essentially normalizes the whole matrix, so to speak. Which is something we have to do because we use neural networks, and AIs and neural networks only understand values between 1 and -1. So now we want to use the non-linear activations, which I also talked about before, which will create a complex mappings between the module's inputs and outputs. They are applied after linear transformations to introduce non-linearity, helping neural networks to learn a wide variety of phenomena. In this module we use nnn.relu between our linear layers, but there is others activations to introduce non-linearity in your module. So this is something you have to test with, and essentially see what type of non-linear functions that works for you. And I'm just gonna check the time. Okay, so that's what you have to do. So let's just check how this works. So here's basically RLU. They actually explain this really well. So this will create a linear function in the negative quadrant here, and then create a non-linear function in the, what's up, Daewang, yeah. This will create essentially a non-linear function in the positive quadrant. And this is what they essentially do. So they create a RLU, and then we use random input, and we essentially just input the input to the value and get an output, and then they just print the function, I guess. So this is basically how value works, and if we have other how do you say it, batches here, you will essentially just get a differentiation on this part of the function. So that's really good to know. I will probably create a better animation for you guys, so it will be a lot clearer. Alright, so we create a nonlinear activation for the complex mappings between the modules inputs and output. They are applied after linear transformation to introduce nonlinearity, helping neural networks to learn a variety of phenomena, which is fine. So let's just copy this and see if we can, and I will explain. I highly recommend you guys go in here and read this document here, because this will essentially also explain it to you guys a lot better as well. So let's test this out. Okay, so before the value, we essentially have this type of matrix here, and then if we check off the value, we have a different matrix. So this actually created a function that adjusted it by itself, depending on the batch sizes that we had. So that's really cool. And now we have the element of sequential, which is an ordered container of modules. So here you can have multiple modules that is ordered by stages, I guess. So the data is passed through all the modules in the same order as defined. You can use sequential containers to put together a quick network like sequential modules, essentially. So what this essentially does is... Oops. What this will do is essentially... I think I can actually just... Never mind. Let's have that one. So what this will do is essentially just create a sequential array which have different type of modules inside of it, and then it will use that data that you used as inputs to all the different modules in order. So let's just copy this code here as well. Just like that. And move that back a bit. So we essentially just create a sequence of modules that will get the input in a sequential order, and then execute these stuff. So this is really helpful if you want to just create a simple network with a sequence of different modules or layers. So that's really cool. And then we have the softmax function. So the last linear layer of the neural network returns logits, raw values, which is between -infinity to infinity, which are passed to the nnn.softmax module. The logits are scaled to values between 0 and 1, representing the module's predicted probabilities for each class. The dimension parameter indicates that the dimension along which values must sum to 1. So this essentially is just creating a softmax function for us to normalize the values. And it's not a fancy thing, to be honest. And I think I just... never mind. I did correct there. Just like that. Yeah. So this will just create a normalization for the values. We can actually print the values if you guys want to see. Boom. So let's do that. And then you see the values in this matrix here is in fact between 0 and 1. So this is where you can see the values, and this will essentially create the different probabilities for the different layers. And we also used softmax function based on the sequential array of modules that we used before. So we use multiple layers of different linear and non-linear layers, and then we essentially just use softmax to create the different probabilities that we need. So that's how softmax work. It's not a big thing, it's just a normalization tool that you want to use. And then we have the module parameters. So many layers inside of a neural network are parameterized. I have associated weights and biases that are optimized during training. Subclassing the NNN.module automatically tracks all fields defined inside your module object and makes all parameters accessible using your module's parameters and named parameter methods. In this example, we iterate over each parameter and print its size and preview its values. So let's do that and see, because we can have multiple parameters inside of your custom neural network that does several things. So let's check that out. So we print the module here, and then we just iterate over the different names, parameters, and so on. So let's do that. And here you guys can see the different layers and so on. I will make this a bit bigger. So here you have the module structure, so to speak. And this will essentially just show you that you have a linear module here, a non-linear module here, a linear module here, a non-linear module here, and also a linear module here. And then we also have our parameters, so to speak, that we use. So in this layer, which is the linear value stack by 0 by weight, so we use a size of torch size of this size here, and then the value is essentially this whole tensor, which you can see here. So we input the size and also the values of that tensor. Really cool. And then we have our next value stack, which is the bias. So we have weights and biases, and this is another stack which we have weights and biases, and this is another stack which we have biases. So we have 3 stacks essentially that we use. So this is a really interesting thing. You can essentially understand how if you know how a classic neural network look like, then you understand what this means. And I can actually show you how a classic neural network look like. So I just talked about weights and biases and stuff, and what is that? And if we check on this image here, probably this will probably show you. Let's see, reject. Can I zoom in here? Yeah, I can. That's fine. So here we have our input layer, and then we have our hidden layers as here, and then we have our output layers. And the weights and biases and so on is essentially, the weights is correlating to the different strings between these nodes. So the weight is a number that you use to calculate and predict certain values that is correlating to this specific string or connection between this node and this node. And as you can see, all the nodes is connected to each other, so they think they can send data between each other and think. And just a side note here, this network here actually shows a module based on our human brain. So that's really cool. So this weight is essentially giving this connection a weight, and the bias is just a constant that you add to the weight, essentially, which is just constant over over the different layers and so on. So that's how neural networks basically function, and there's a lot of other data that you probably want to know, but then we get into the really hard stuff about this. But yeah, so this section is basically done. I will copy this code in here, I guess. This is not working out for me, dude. Nice. Bada bing, bada boom. Nice. Okay, that's done. So let's go and check for the other section. So now we have automatic differentiation with torch.autograd. Okay. When training neural networks, the most frequently used algorithm is backpropagation. Now, what is backpropagation? Let's check that out. Backpropagation is essentially, in machine learning, backpropagation is a gradient estimation method used to train neural network modules. The gradient estimate is used by the optimization algorithm to compute the network parameter updates. It is an efficient application of the chain rule to neural network. It is also known as the reverse mode of automatic differentiation or reverse accumulation due to SEPU whatever. The term backpropagation, propagating error correction, was introduced in 1962 by Frank Rosenblatt, but he did not know how to implement this, even though Henry J. Kelly had a continuous precursor of backpropagation already in 1960 in the context of control theory. So this, by the way, just a side note here as well, here you can see how long we have actually known about neural networks, and this is probably even we probably even know about neural networks before like 1930 or something. So neural networks is not an AI is not a new thing, just so you guys know. We actually knew about this in 1930. Either way, so this is basically the whole math thing. I'm not gonna go through this. And then you have all the different matrix multiplications. This is the things you have to know if you want to create your own neural network library, and it's quite fun actually. No, it's not. Okay, so let's carry on, and I will remove this rally explanation as well. Okay, so when training neural networks, the most frequently used algorithm is backpropagation. In this algorithm, parameters, model weights are adjusted according to the gradient of the loss function with respect to the given parameter. To compute those gradients, Pytorch has a built-in differentiation engine called Torch Autograd. It supports automatic computation of gradient for any computational graph. Consider the simplest one-layer neural network with input x, parameter w and b, and some loss function. It can be defined in Pytorch as the following manner. Okay, so we also import torch, and then we create. We can actually see this. Let's test this out actually in our code. So I will comment this out because we don't need this, and then we just import torch. I think we already have done that up here, so I don't think we need to do it again. Fine, and let's just print the different layers to see what is actually happening. I'm gonna print the W here as well, and print the B here as well, and we also want to print C and the loss. So this is basically the different parameters that we have, and let's print those. Okay, so here we have, so we also create a tensor with a lot of different ones, which have the dimension of 5. Let's print the size of this to see what happens. Okay, so the size of this, okay, it's 5, it doesn't really matter. Let's forget that and clear this and print the values again, just to see what happens. So we create a tensor of just ones with a dimension of 5. We also create a tensor with zeros of dimension of 3, as you can see here. And then we create a random tensor with dimension of 3 that we with a dimension of 5. My bad. In the so it's 5 by 3 essentially. Yeah, 5 by 3 tensor. That requires the autograd, which is true. And then we create another with a dimension of 3 that requires the autograd to be true as well. So we create different tensors that requires this grad to be true, which means that it can be used to use backpropagation functions. And then we use math.multiplication with x and w, so we multiply the different tensors by each other and then just add the next value. So this is essentially a linear matrix or linear function, I guess, because we have a k value multiplied with the x value and then added with a standard value. And then we just print the loss, or we just find the loss with z, which is the linear matrix function, and also the zero matrix. So that's basically what we do. I won't use this though, because this is just a formal explanation of what the backpropagation does. So tensor functions and computational graph. This code defines the following computational graph. So we input an x, which is essentially here. Let's remove these. So we input an x here, and then we essentially add the parameters w and b, and then we get the z. So we multiply with w, and the w is this thing here, which is w. So we multiply w with x, and this can we see here, and then we add the b matrix here, which is this thing here. So we multiply with the w matrix, and then we add the b matrix, which is the parameters, and then we get the z matrix, and then we essentially use ze, which is computational it's computational it's basically just a function where we take in y and then we get the loss. So this is a function that gets the loss, which is binary cross entropy with logic. So this is basically calculating the binary cross entropy between target and input logics. I'm not gonna go into too deep on that. So yeah, that's basically what that does. In this network, w and b are parameters which we need to optimize. Thus, we need to be able to compute the gradient of loss function with respect to those variables. In order to do that, we see that we require the grad property of those tensors. And there's also a note. You can see that the value of requires grad when creating a tensor, or later by using x.requires.grad equals to true, which we essentially could also see here as well. A function that we apply to tensor to construct computational graph is in fact an object of class function. Okay, so a function that we apply to tensor to construct computational graph is in fact an object of class function. This object knows how to compute the function in the forward direction and also how to compute its derivative during the backward backward propagation step. A reference to the backward propagation function is stored in the grad fn property of a tensor. You can find more information of function in the documentation. So this is the gradient function for z, and this is the gradient function for the loss. Let's try to show you guys these. Let's remove these prints here because we don't need these. Okay, so here you have the different functions, and so you have this object at this reference, and this binary cross entropy with log its backward object to this reference. So you can see that we add this object to this reference, and then we use this function object as to this reference. It's a very interesting way to use this kind of. Either way, so we're gonna compute the gradients. To optimize weights of parameters in neural networks, we need to compute derivatives of our loss function with respect to parameters. Namely, we need the loss and the loss of under some fixed values x and y. To compute those derivatives, we call loss.backward and then retrieve the values from w.grad and b.grad. So we just do this instead. Actually, we just can calculate the backward, compute the gradient of the current tensor with graph leaves. The graph is differentiated using the chain rule. If the tensor is non-scalar, its data has more than one element and requires gradient, the function additionally requires specifying gradient. It should be a tensor of matching type and location that contains the gradient of differentiated function, whatever. So that's this is basically just calculating the different gradients of the tensor. It's nothing fancy, to be honest. Disabling gradients tracking. By default, all tensors requires grad through our tracking, their computational history, and support gradient computation. However, there are some cases when we do not need that. For example, when we have trained the module and just want to apply it to some input data, and we only want to do forward computation through the network. We can stop tracking computations by surrounding our computation code with torch.nograd block. So if we don't want to retrain the whole neural network, we essentially don't need this gradient thing. So we can disable it essentially. So here you can just torch.matplotlib and then see the different torch.grad. But if we want to retrain the neural network, then we have to add that. And yeah, I think that's optional reading tensor gradients, and we don't need to know that. That's basically it. And then you have optimizing module parameters. I just want to check deep learning with Pytorch in 60 minutes. Blades, image and video, torch vision object, nice. Audio, I'm just checking the different things. Okay, so optimizing module parameters. We know that we have a module. Let's actually add this header. So let's add that here. I will actually go through this later. I'm actually gonna stop here and because it's getting really hot inside of here. I'm sweating right now. And I think that's all for today. I might actually go back to streaming later today. I will see. But this is just checking how to optimize module parameters and training the whole thing, I guess. let's see, yeah, so they train and optimizing the parameters and training the whole thing, and then they get an accuracy of 71% and average loss of 78%, which is not too bad, but definitely not the best states or status you want. But let's do that either tomorrow or today, I think. Yeah, let's do that. Either way, guys, I hope you enjoyed this stream, and thank you for watching.